Next up, we have Michael Picco, who is president of the Picco Group. Thank you.
Thank you. Can you hear me okay? I'm the president of Picco Engineering. We're a facade engineering company, full structural service, but our focus is really on facades and with a particular focus on natural stone. My presentation is going to be a little more technical with a few examples. I'm going to talk about the collaborative approach and the importance of that, especially in complex facades, and we've seen quite a few of them already today. Some design solutions that meet the complex demands of architecture today, and then some examples, a few case studies and some examples of projects we've worked on. So we'll get right into it. I mean, the collaborative approach is extremely important, and when does that happen and who does it happen with, I think is extremely important in designing the success of a project. Building a team that's aligned with complementary skill sets depending on the project demands, again, is very important, and this may not only be consultants, it may involve fabricators, installers, manufacturers that are part of the process very early on. And collaborating with the necessary information. How are we going to communicate with each other? How are we going to resolve solutions together? All that is very important in the early stages of the design. And schedules and budgets obviously are important in that. How do our decisions affect these things, which are always very important? So the earlier we get the key stakeholders together and make sure we have the right ones involved, usually determines the success of the project. We get involved with many projects. Here's a stone project that we got involved with, and the contractor started raising some concerns on about the way the stone seemed to be chipping very easily, and it looked like raising concerns about some of that on the job site. So they called us in, and first thing we did was, do you have proper test data on the stone? Which they had test data that was like 8 years old. So, well, that's not proper test data. We need to test the stone we have on site. So we went through some testing, and we actually determined it was a very soft, high absorbing limestone, not really suitable for this application. The problem was there was $2 million of stone on the job site already. So the owner said, no, you got to make that stone work. So we went through an extensive testing program, developed a pretty complicated connection, and you can see how wide that tab needs to be into the stone because the stone strength was quite weak. In order to meet the demands of the loading on the building, we had to design a pretty complicated anchor, which could have easily been resolved if we were involved with the project a lot earlier, or proper people involved with it earlier, not when you have $2 million of stone on the job site. So we did come up with a solution. It did cost them a lot of money, and it costed them a lot of time at that point. So this is why we say it's extremely important to get into some design assist early on. One of the other presenters spoke about the importance of the material selection and the process they went through in doing that, and we get involved in a lot of that very early on. So part of our job is to vet and validate and suggest the best solutions for the particular application. When we get involved with Design Assist, we've developed a bit of a checklist of the important items that we feel are necessary. And some of them include, constructability review, practicality, things affecting budget, installation, scaffolding, access, all those things that play into the role of the decision-making early. Structural coordination is extremely important with facades. We get involved with facade design a lot of times when the structure is already designed. So what's the slab edge deflection? What assumptions has the structural engineer made on that slab edge that may limit us in our solutions? So if we're involved early, we could influence some of those decisions on the main structure of the building. Things like deflection at the slab edge. How is that transferred out to the facade? How do we deal with that? On long spans, is it worth designing the structure a little stronger to limit the deflections on the slab edge to help the facade? So these are some of the things we work through as a team to find the best solutions. So building movements. In seismic zones, horizontal story drifts that we have to deal with. How are we translating that out to the facade? Backup structure, what's the best material? What do we need to anchor to? Are we anchoring to the slab edge spanning floor to floor on the facades? Are we using light gauge metal stud infill framing to attach to? These are all decisions, again, that influence the final product. And of course, physical mock-ups are always a great way to vet out proof of concepts. So, and preliminary engineering and sizing of some of the primary elements are also go into that first process. So let's see a few, actually, before I get into examples, meeting the demands of architecture and complex designs now. Well, obviously, the advent of BIM has really expanded the abilities of creativity, and manufacturing advancements and fabrication advancements with the use of robotics, CNC equipment, things that weren't feasible even 10 or 15 years ago, now are cost-effective solutions that you can do with robotics and CNC technology. So we encourage architects to continue to push the limits, continue to get creative, and find ways to make things happen. Here's the Apple headquarters in Cupertino that we worked on, and you can see some of the stone fabrication and the sharp edges and curves that you could get now with the fabrication equipment that's available. That's an integrated handrail, all carved out of cubic marble blocks, and all vein fitted together, and extremely tight tolerances, with all the radii meeting the radii of the iPhone. So interesting, but with these complex structures, we also have to get into deeper analysis and make sure that we don't run into problems down the road. So making sure we're properly vetting all the materials, properly vetting the installation methods, and obviously schedules and construction demands are always something that we all have to deal with. Decisions need to be made very quickly, and that's always a challenge as well. Here's the Museum of Natural History in New York City, a curved facade. The original intent of that was to go with flat faceted panels because that was thought to be the most economical way to approach that design, when in fact, again, with CNC technology, making those panels curved was not that much more expensive than going with flat faceted panels, and that was the decision that was made. Sustainability, I mean, a lot of people are talking about that. We've already heard about it. I'm not going to speak too much about that. Only, is it really important, and do we have the right information to make those decisions? I still see owners making decisions on cost, not necessarily sustainability. So again, trying to find that right balance. Is it really important? Do we have the proper information? You can see EPDs and life cycle assessments that give you totally different values depending on who's publishing the data. Again, do you have the right information in making those decisions? So innovative engineering facades. So we've already seen this project. Hamid showed this one. The National Music Center in Calgary. Firstly, we got into some preliminary design on establishing the appropriate panel sizes of the facade in order to meet the geometry needs and the curves that the architect had designed into it. The interesting thing about this building is all the walls are square at the bottom and they're all curved at the top. So how do we develop this facade to create those curves and transitions from the square base to the curved top? So the approach was to go with a light gauge stud framing, and you can see on the right-hand side there the plan views at each level at one of the corners. So you start with flat on the bottom, and you can see the radii continuing to grow as you go up the building, and then there's an elevation of the facade there. So the corners became very complex. Some of the details on how to frame it and how to create the curves was a real challenge. The other challenge was limitation on the slab edge. Engineers said you can't have any moment developed on the slab edge, only vertical, horizontal loads. So we had to come up with a system there to do that. And what we did was we developed a moment connection onto the stud. Through that, you can see we've developed a circular pattern of the screws that could accommodate all the various angles that we were going to deal with as we went up the building. So that became kind of a universal connection, with the exception of some special connections that were needed in special areas. But it worked for the majority of the connections, and the connection back to the slab was a true pin connection, basically a pin into the slab with a retainer to keep it down, but that was it. And it was very effective, and we had a slip connection just above that could accommodate building movements that, again, needed to translate out to the facade. The other challenge was, how do we get the installer to put all these studs in the right place? So again, a lot of collaboration with the surveyor, the GC, the installer. Okay, how are we going to give you the information you need to install these all correctly? What we did was we had an XYZ coordinate for every single stud at every slab level. And what we actually had to do to create the geometry on some of those studs was actually twist them as they went up. So we had stud location at the bottom. The survey surveyed an offset for each of them, and every single stud was laid out on the slab so they could measure out the XYZ. The XYZ was established by the surveyor, and all they had to do was measure out and follow parallel to that line at each level, and then lock it in. So that's what we did there, and you can see how the studs are not continuous, because as we went up the building, we had to add more studs because the walls kept growing. So we created a very large track to receive the lower studs and start the new studs, and then you had slip connections for the upper ones and locked in the lower ones. So a little bit of a challenge, but everybody collaborated very early. We came up with very simple solutions, and it was executed fantastically. And you can see the finished product there of how smooth all those curves turned out at the end. Another example is Temple University. This is a crust-faced granite clad job, ventilated rain screen with aluminum support system. This was 5 3/4 inch wide granite strips with a crust face on them, a very rough texture with slots. And because the strips were very narrow, we could only have one connection top and bottom on each piece. So we developed a vertical rail system with horizontals and tried to make as many of the panels as typical as we can that we could hook in, and try and make it economical by making it look random but making it as typical as we can at the same time. So here's a few photos of the crust-faced granite there on the facade, the vertical mullions that were spaced about 1,200 millimeter on center, and then some of the horizontal rails with the stone panels installed there. And the verticals were all pre-assembled on the ground with all the clips in place at the proper spacing based on the shop drawings, so they didn't need to do any of that up on the scaffold. It was all pre-assembled. The drawings you can see that were developed, blow up on the right-hand side, load-bearing connections up close to the top with all the panels hanging down, with slip connections to take thermal movements and building movements. So very important to consider the movements in the facades here. And again, you can see the finished product there. Third example, very simple looking building, flat walls, rectangular panels. This is we refer to it to the MCCCH building because it's a bit of a tongue twister when you try and say Multnomah County Central Courthouse. So it's the MCCH, Portland, Oregon. It looks like a very simple flat facade. It's nothing but that. 40 millimeter limestone was selected, open joint ventilated rain screen, very contemporary design, but it's a high seismic zone. So we developed a thermally broken vertical mullion, and it received a Kingspan panel, so it was fully insulated. And you can see the connection at each slab edge there to take the building movements for seismic activity. 3-inch interstory drift, 3-inch movement from floor to floor horizontally. That's what we had to pick up on the facade. So that was the big challenge here. The rest of the building wasn't so bad, but the corners and how to deal with corners and 3 inches of movement from one floor to the next. So what we did was we isolated the corner, created a hinge, literally a hinge with 2 pivot points on those panels on the corner. And we modeled it, and it should work. So let's, full-scale mock-up. And we did a full-scale mock-up here. You could see the structural performance. You can see how the corner panel's pivoting. And then there was a full dynamic water penetration test and air infiltration done as well after the seismic movements. And we racked that thing to 3 inches, brought it back to normal, and there were no cracks. Everything went back to position. They had the ability to push it to 4.5 inches, so we said, why not? Let's give it a go. So they pushed it to 4.5 inches. A few panels cracked, but nothing fell off. So we were pretty happy with that. And, so you look at some of these buildings, they look pretty simple in nature, flat. Oh, that's an easy facade. There was a little more into it that you don't see in the finished product. Now I'll just quickly run through a few other examples of different facades we work on. Vanderbilt University was more of a traditional brick and stone type project. There were 7 chimneys, all different design. We built them all on the ground and we hoisted them up. They were the first stone elements put on the building. It allowed them to completely waterproof, put the roofing membranes on before any of the brick and stone work got going on the building. So it was a really effective way for the contractor to get a head start and also not have all these building materials on site at the end of the project, bringing up mortar and dirtying all the materials that you would have at the end of the project when that would typically be done. Large format thin panels, we've got some people here, we work with them as well. The challenge with those is multiple back anchors because we're dealing with very thin materials, structural limits on wind loads. Sometimes you have 16 or 20 anchors at the back, and we call them blind anchors because they need to slot in. So the QC on the installation, the placements of the rails are extremely important because those panels go in and they drop in, and they all need to engage. And we've seen a couple of failures where some of those rails are not in the right spot. Those mid anchors don't engage and they overstress the other anchors. So just a word of caution. We work with these materials, we engineer them, but that's something that we bring up very clearly at the beginning, the QC of the installation, very, very important. Another terracotta facade on the top there, that's Gusto 501, that's a restaurant in Toronto. Traditional clay tiles, just installed in an interesting pattern with cuts on it. Some of those are actually cantilevered 2 feet out from the main wall. So we had some pretty high eccentricity on the wall and the whole design, but we did some mock-ups and it turned out fantastic as well. Latter-day Saints Temple at the bottom, we've worked on several of these. They like their natural stone. They use a lot of stone on their cathedrals and churches. This was actually a prefabricated steel structure, so the structure came in all in sections with inserts built into it to receive the framing for the stone installation, and then a traditional hand-set stone for most of it, although we are panelizing a lot of the stone on the towers, similar to what we've done on Vanderbilt, with able to build it on the ground and hoist it up in place rather than hauling all the material up there. Air and Space Museum in Washington, D.C. is a full reclad and upgrade on thermal and blast resistance. That's, again, a vertical aluminum system. In the reclad, they decided they didn't want to reinforce every floor. The panels were traditionally going floor to floor. In this case, they said, we're only doing the 3rd level, you got to hang all your stone off that. So we're hanging, our mullions are in tension, 60 feet long, hanging all the stone off the 3rd floor. So another interesting design that looks very simple, but there were some challenges there. And, the last one there is a brick design that we created with a screen. We designed a special brick with 2 holes in it only, and we ran reinforcing rods through to create kind of an open screen there with a steel frame around it. And it looks like basically a traditional brick installation, but a little bit of character to it. So that concludes my presentation. I had 20 minutes. I think I'm right on the clock. I tried to talk very fast and cover a lot of topics. But again, we love getting involved with complex projects. We love getting involved with being challenged on new things. And there's always solutions if we bring the right people to the table early on. And that's really the message I want to deliver here is collaborating with the right stakeholders early on. We can overcome any problems. And thank you very much for your attention today.